Hey, what's going on, everybody? Today I'm going to go over, hopefully, almost everything you need to know about a home network, what's happening behind the scenes, a little bit of how it works. I'll be talking through just kind of what's in a typical home network, what it does, a little bit of how it's set up, and kind of the different configurations that you might see and how you would really manage it. So buckle up, this is going to be a pretty long one, and I will say that if you are pretty familiar with computer networking, maybe you might want to skip this video. I'm going to be going over some of the basics, but basically we're going to see how traffic flows through a network, what services are required, and all of that. So if you're not too curious about any of that, then I apologize, but let's go ahead and just kind of get into it. So we're going to be talking about some of the basic equipment, and mainly that's going to be like your router, your PCs that you're using with your network. And we're going to be breaking these down a little bit because mostly people have a all-in-one router, which is actually not just a router. We're going to be getting into kind of what the words technically mean. Just because you go and you buy a router from Walmart or your ISP gives you a router doesn't really mean that device is purely a router. There's a lot of other stuff going on with it that when you get into the world of like enterprise networking, each of those parts is technically like its own device. So speaking of that, let's go ahead and just jump right into the good old boring terminology, and we'll just go ahead and start with a router. So by definition, a router is just really something that routes traffic based on IP addresses. And your IP in your typical home network is usually something like 192.168.0. Whatever. That's your pretty standard home network IP address range. And this is very important because routers deal with IP addresses. That is how they route. That is what they route. And that is pretty much what everything else that a router does will revolve around. Now, we call routers layer 3 devices, and this is just a layer of what's called the OSI model. That's something that if you study computer networking, you're probably going to see. It's just this like model breakdown thing of the different segments of how a computer network functions. There are certain services, certain devices, certain ways that things talk to each other depending on what layer of this model you're at. A router just happens to be layer 3. Which is where you're dealing with IP addresses. Now there are other functions that a router will usually take care of, such as NAT or network address translation. We'll kind of get into this a little bit later. But how a router really works is it maintains a list, which is called a routing table. And that's pretty much just a list of a whole bunch of networks and what's called their next hop address. And they're all with IPs. So for example, your routing table might look something like, well, like this. And this is a super simplified way of showing a routing table, but you got like 192.168.0.0. Your home network can be accessed via interface 1. So it's going to send everything for that network out interface 1. And if it gets anything for 10.0.0.0, send that to 192.168.0.1. And this is kind of like a map, just pointing networks towards either another router's IP address or a certain interface. That's like the router knows that that network might be located over there, or at least that next router knows how to get to it. Now the next thing that we're going to talk about is a switch. And by definition, it's just something that directs traffic based on a MAC address. So it doesn't look at, nor does it care about IP addresses at all. And switches are located at layer 2 of that OSI model, in case you care. And switches also take care of what are called VLANs. Now we're not going to get into those right now, but that is where these live. Those are just virtual local area networks. And it's a way that switches isolate traffic for different layer 3 networks. Now switches deal with what are called MAC addresses instead of IP addresses. And it makes a list just like a routing table, except for that's called a MAC address table. And instead of it being like network and the next hop IP address, this MAC address table is really a MAC address and what port on the switch that MAC address is located at. So your MAC address table would be something like PC1 located on port 1, PC4 located port 4, and so on. And this is how a switch knows where to send traffic for a certain device. It keeps this table of MAC address to port associations. And I don't know how many people are still familiar with hubs, but it used to be that the differentiating way to think about like a switch versus a hub is that a hub just sends everything out every port. It just duplicates everything. But a switch is smarter. It maintains this table. When it receives traffic for a certain MAC address, it typically knows where to send it as long as that MAC address is in its MAC address table. And if it's not in there, then the switch will selectively flood that out all of its other ports and see if it gets a response. And when it does, it adds that to its table. But the main takeaway here is switch equals MAC addresses, has nothing to do with IP addresses. And these are the devices that typically have quite a few ports. So where a typical like router may have 3 ports, and we're talking about like a legit routing only router, not an all-in-one device that you would see in your home. And then switches are more like what's on the back of your router device at home, where there's multiple. There might be like 5 or 8 or 16 or up to 48. Switches are where you really connect the bulk majority of your devices. Because one rule on a router, which I didn't mention, is that each interface is technically supposed to be its own network. It's actually impossible to configure 2 interfaces on the same network on a real legit router. And those devices, like the all-in-one that I keep mentioning, just have like both of these operations bundled together. You're technically plugging into a switch that interfaces with a router within the same box. Now the next thing that we're going to go over is server. Now if you're like me, somebody says the server, you're probably thinking of this real large metal box that is in a data center somewhere, like a huge computer. That is the server, the mainframe. Well, really anything that serves or hosts any kind of service is called a server. So the term is pretty relative. So if something has a service that another computer or device or whatever is going to use, then really that device becomes a server. And most of the services are just kind of to make life easier, but a lot of the services for a home network are actually like requirements. Like you can't really function a home network without these services. And examples of these, because I'm sure you're like, what are you talking about, would be something like a DNS server, a DHCP server, or probably the most popular, just a web server. Now technically, if you have an all-in-one device, here we are going back to that router again, these are all bundled onto that box. DNS is built into that device, DHCP also built into it, and web server, yep, it has one because that is what you connect to actually configure it. So when you browse to your router or whatever, you are using the web server service of that device. And that is a pretty basic one. But the reason that I kind of just go over these terms is if you think of a server as the huge metal box, technically you are correct. That server device serves a lot of services, but your server can be literally the computer that you are even working on. Or shoot, if you enable the right services on your phone and end up using it from another computer or another phone that is not that one, then it has become a server. And while like an all-in-one router will have all of these services built into it, DNS, DHCP, web server, you can separate them. They don't all have to be on that device. You could have a different device to be a server for that specific service. Now, with that out of the way, the last thing I'm going to talk about, at least for terminology, is modem. And this is probably both the most basic and one of the most difficult to wrap your head around, I guess. but modem literally stands for modulate and demodulate. And this is the device that converts the Ethernet, which is the protocol that pretty much all your home devices are going to use to communicate, into some other protocol, which actually like talks back to your service provider and allows you the connection to the rest of the world. So Ethernet, while that's used by most everything, it has distance limitations. Like you can't just use an Ethernet cable from your house to your ISP. The protocol is just not designed to work like that. And there's other ways to get that signal from your house back to your ISP and across the entire world. And typically you see like the three major ones, like DSL or cable, or nowadays fiber. Now, each of these technically has multiple sub-protocols that they can use, but these are like the three main categories. So all your modem does is take your Ethernet traffic coming from your home network and convert it to one of the major protocols to communicate with the rest of the world, send that to your ISP, and then return traffic coming back in will be converted from one of these three protocols back into Ethernet. It just facilitates the conversion between the different methods needed for both of these purposes. And a lot of the confusion comes in where like modems are typically built into the routers that your service provider will give you. So a lot of people will be like, well, you need to reboot the modem, or it might be a problem with the modem, or could be a problem with the router, you need to reboot the router. And a lot of times they could be talking about the exact same thing, but also a lot of all-in-one routers don't include a modem. So you do have to watch out that the device that you're getting is doing everything you need it to do, if that makes sense. Now, that's all of the terminology that we are going to go over, at least for now. But talking about those different all-in-one devices or services spread out, let's just kind of visualize this a little bit. So the main one that I've been talking about so far is like your all-in-one device, which is where all of the services and all of the networking functions are just bundled down into a single box. You plug in the cable from your ISP and do a little bit of minimal setup, and then you access the internet by either connecting to wireless or plugging in a cable directly to this device. But on this device, you've got your modem, your router, maybe a firewall, a DNS and DHCP server, and a web server probably, a wireless access point, and a switch. So this is why it's called an all-in-one device. All of these different networking functions are built into this one little box. And it is super convenient for you, but also having all of these different functions in the same device opens it up for any one of these to fail and affect all of the others. So these all-in-one devices are really kind of like jack of all trades, master of none, and that's usually why you have to reboot them most of the time when they just randomly stop working, because one of these services or functions decided to go haywire. Now, probably the second most common setup that you see is a modem and a router separately. So a lot of times your ISP will just give you the modem, and maybe it's up to you to provide the router, or they just give it to you in two separate devices. So the connection that goes back to your service provider connects to your modem box, and then your modem connects to your router. And all that really does is it removes that modem function from your router box and puts it on its own. And this gives you the ability to upgrade, downgrade, switch out, or whatever you need to do with the modem function without affecting or having to touch any of your other stuff. And this setup used to be probably the most common, and it still is for like business connections especially, except for nowadays usually the business connections are moving to something what's called a NID, which is just a network interface device. All it is a managed modem, really. Just the names have kind of changed, because typically the NIDs nowadays are dealing with fiber, but it's still a fiber modem. And then another kind of more common setup is if you have a modem and then maybe a router which does not do wireless. So take out the wireless access point portion of that router and put that on its own device. and the way that a wireless access point works. It doesn't route, doesn't do any of that stuff. It's literally kind of, you can think of it as a wireless switch. It is still mainly focused on MAC addresses, and it's just a gateway to get wireless clients to connect to your wired network. Now, the next kind of topology that I'll talk about is one that's not common in homes, is a lot more common in larger like enterprise environments, but what I call it is the full-blown separate device approach, and that is where you've literally got a different device for everything. So you've got your modem, and then you have just a pure router, and there are a lot of routers that have the firewall built into it if you're going to have one. There are some just like pure firewalls, but we're not going to get into that. You got your router and your switch, which is where you've got your PCs, and then you've also got an actual like server appliance which will serve your DNS and your DHCP, and then you've also got here somewhere your wireless access point, which is how your wireless devices connect, and then maybe like another server over here for your web server or whatever. So anyways, the main point is that each of these things that would really be in your one device in your home network are all broken out into separate physical devices. And your home network might have the same thing. There's a lot of pros and cons to each method of doing this. When you have separate devices for everything, your reliability generally goes up, but so does your amount of work needed to manage everything. So now that we've seen kind of the common layouts and methods and know a little bit what we mean when we're talking about routing, switching, modems, all that kind of stuff, let's take a look at how the network actually functions and what each of these have to do with each of the others, what it all means. Why do you need all these? And to explain this, I am just going to start with going over some of the layers of a network. Now, I apologize, this might get pretty overwhelming pretty quickly, but just try to bear with me through this. It might make sense at the end. Basically, people that study networks use what's called the OSI model for data communication. It's got 7 layers. We're really only going to concern ourselves with the first 3 just to get the building blocks out of the way. And basically all this is layer 1 is defined pretty much as your cabling, or how devices are physically connected to your network. So your Ethernet cables that plug into your computer, or go between your switch and your router, or connect to your ISP, even your wireless, technically radio waves, that's a physical thing that is providing the connection for devices. These are all layer 1, and they have to exist for things to communicate. And you break out the standards in here through many different standards, but just think a cable, an Ethernet cable, there's a standard for how many twists are supposed to be in it, how many pins are supposed to be on the connector, what order the wires are in. This is kind of like what we're talking about when we talk about layer 1. There's all kinds of rules for the actual physical connections for these devices, which will carry these signals for other layers. And next we've got layer 2, which is called the data link layer. You can just think of it as where switches are. I just realized I kind of got these backwards. Physical is the real name for layer 1, while data link is the real name for layer 2. And my drawing tablet here has decided to wig out, so everything looks really ridiculous. Now, like we've already said, data link layer, this is where switches operate at. And this is technically where your local area network is defined. Pretty much everything that operates at layer 2 is going to be in the same local area network. And communication happens through MAC addresses, not IP addresses. And the unit of data at this layer is technically called a frame. You may have heard something like, oh, we're sending packets. Everything on the internet is a packet. Technically, that's not true. A packet is what we call data at layer 3. A frame is layer 2. And shoot, I think electricity or bits are what we call things at layer 1. And I promise that this will make sense in a minute. We're just still getting there. There's a lot of background to really explaining this kind of stuff. and a lot of it is very boring and will put you to sleep very fast. Now, this MAC address I've been talking about is an address that's pretty much burnt into every device. Technically, every electronic Ethernet device in the world should have its own unique MAC address, and there are standards on how these are applied. You can actually look up a MAC address online, and because of the different parts of it, you can tell who the vendor is. But we're not going to get into that. For these purposes, what we have is an address that looks basically like this, and this is technically all we need to communicate at layer 2 is this MAC address. If you're curious, it's 16 bits written in hexadecimal. That part doesn't really matter too much. And I just realized I think I said 16 bits. It's not, it's 48. I think what I meant was there's 16 bits in each of the thirds. Anyways, if you were writing that down, it is not a 16-bit address, it's a 48. Now, moving on, layer 3. This is the one that you're probably the most familiar with and where most of the terminology and stuff comes from when we're talking about networks. And yep, this is where routing occurs, or your routers sit. And that's why we call it a router, because it routes IP addresses at layer 3. And this is where your good old IP addresses come into play. So just like every device has a unique MAC address for layer 2, each device on the internet's got to have a unique IP address. And like we've already drawn out, this is probably one of the most common ones that you're ever going to see. 192.168.1.1 or 0.1. They're both probably equally used as much. I'm not going to get into what makes up an IP address, which is basically how to subnet, but I will say IP addresses are broken apart into many different subnets, and it's a router's job to route between all of the different networks or subnets. And the reason that they're called subnets or subnetworks is that IP addresses can be broken down into either a class-based system, if you're thinking a long time ago. Nowadays, it's called a classless-based system. But anyways, they're broken down into two different parts. There's what's called the network and then your host. So in a typical home network, 192.168.1 is typically your network, and your network IP address would be 1.0, but all of your devices on your home network will have a different host address, and that's the 192.168.1.1 or 1.10 or 1.25, anything between 1 and 254, in the way that a typical standard home IP address would be broken down. Like I said, I'm not getting into the subnetting portion of that. Basically, just know that there's your network portion, which basically defines your entire network, and then there's your host portion, which is the address that each of your hosts gets. Now, a major part of these IP addresses and even MAC addresses is that there can't be two duplicate networks or two duplicate IP addresses really anywhere. Everything's got to be unique, or your data is going to end up in the wrong place. And I guess I'll take a minute here to talk about what's called private addresses, since it's very important and it plays into one of the most vital parts of a network. There's actually 3 subnets of IP addresses that are designated as private. And all this means is that they're not going to work on the public internet. They are for internal use only, and these are the subnets that you see in every home network. That is that 192.168.0 network. It is the most common private network address, and I really wish that my tablet would draw better. This is making me look like I'm writing at a kindergarten level. This one is split basically half and half between network address and host address range, so you can have 192.168.36.200. That is still in the private address range. Now, as soon as this turns from 192.168 to 192.169, it is outside of that private range. It is now a publicly routable IP address. Now, the other two, if you are curious, is 172.16.0, and then you've got the 10.0.0.0, with the 10 taking all 3 of these for what you can technically use for different hosts. And the 172, you can kind of think of it as the same as the 192.168, except that it's not. Here you actually get into a little bit of subnetting, but we're not going to worry about that. If you see things that look like these 3 addresses, they are private, and they are only going to work within an individual network, not over the public internet. Okay, and I just took a little bit of a break to fix this tablet thing. Hopefully it'll look better now. Anyways, we were talking about private addresses. If you're wondering how this works over the internet when pretty much all the IP addresses you've probably seen are in the private range, it's due to something called NAT, which we will talk about here in a minute. We'll get to see how that works and how it actually takes a whole bunch of private IP addresses and makes them into one public. Now, just a little bit extra, the unit of data at layer 3 is referred to as a packet, which is the one that I'm sure you've heard about. Most people just refer to everything as packets, like I've already said, but technically it's incorrect. But really it's kind of the same thing as referring to every Cat5 cable as an Ethernet cable. Technically there's no such thing as an Ethernet cable, because Ethernet is technically a layer 2 data link protocol. But potato, whatever. Now, each of these layers just kind of adds on more information to the unit of data that it's talking about. So like at layer 2, this is going to get real dumb real fast, but layer 2 you've got like a header and then your data, which the header just contains a source and a destination MAC address. And then once it gets to layer 3, that kind of compartmentalizes, or what we call encapsulates that, and puts its own layer 3 header on it, which includes source and destination IP address, among other things. There's a lot of other stuff that these headers do, and there's also footers, but we're not going to talk about that. And these headers and everything is how traffic gets passed around the network, and depends on which devices that they're hitting as to if they can be understood or not. So like if a device that is only functioning at layer 2, like a switch, has no routing functionality at all, and you give it a packet with a source and a destination IP, it's got no idea what to do with that information. It doesn't care about IP addresses, and it probably doesn't know how to strip that header. And it really doesn't care. Now, it can take that traffic, it'll strip off all of the irrelevant headers, usually, until it gets down to the layer 2 one, but it's only going to be able to change the layer 2 information. Now, for the purposes of this video, we are going to say that every computer or device that wishes to talk on the internet or your network needs the following 4 things: a source MAC address, a destination MAC address, a source IP address, and a destination IP address. This is the most basic form of information that you need to communicate on a computer network, with a whole lot of exceptions and other stuff hidden beyond this. But since we've talked about everything up to this point, and we know that we need these 4 pieces of information, let's start taking a look at how data will actually flow through your network. And here's where we're going to start putting everything together and probably get really confusing. So let's start at the very basic level with our little router all-in-one. We'll say that that's, I'm going to label it router, but it is one of those modem, router, DNS, DHCP, server, switch, everything in one box type deals. And we've got our computer down here, and our router is connected to the internet. So what happens when we plug our computer in for the very first time? Well, our computer, A, is going to try and get an IP address. So it's going to send some information out. Now, at this point, it has like next to nothing in the form of those 4 things that we need to communicate. It does not have a source IP address, because it doesn't have an IP yet, unless we statically assign it one. It doesn't have a destination IP address that it's going to, because it does not know anybody's IP. It does have a source MAC address, but it does not have a destination MAC address. Now, what it does to fill in these missing areas to communicate with DHCP is it sets its source IP to just all zeros, and the DHCP server will know what that means when it gets it. It sets its destination IP address to all 255, So that's 255.255.255.255. And that has to do with how IP addresses work. I've already mentioned that you usually have your network address, which is what we had said before, 192.168.0.0 technically designates your network, but you also have what's called a broadcast address, and that's the very last one in a certain range. So this one would be 192.168.0.255. And because this computer has no idea what network it's on or anything, it sets everything to 255, which is a global broadcast address. That's going to go to every device on the network, which coincidentally is going to hit the DHCP server located on the router, because that is a part of the network. And it's going to do basically the same thing for the destination MAC address. Because it doesn't have one, it's going to set that to all Fs. So just F. And that is pretty much the same thing as a broadcast IP address, just in MAC address form. So when it sends that out to the router's going to get that. It's going to see, well, that's destined for all zeros. What? 255, that does include me. Okay, cool. Source MAC, awesome. This will get registered into the switch's MAC address table. So now it knows PC1 is on port 1 because it's seen that information. It registers that into the table. And then really what designates this being a DHCP request is port 67. We're not going to talk about ports. That is a layer 4 protocol, but pretty much this information runs through the router. It gets to the DHCP process. It gives it an address, and there's a lot of stuff in between. But now let's say our computer got the address 192.168.1.5. That is now our address. So for that whole source destination thing, we now have a source IP address. Our destination IP address we will have when we communicate with something else. We have a source MAC address. The only thing that we're going to be missing pretty much from here on out is going to be our destination MAC address. And that is where things get real special. So just to kind of clean this up for the rest of the examples, our source IP of this computer, 192.168.1.5, and we're just going to designate this computer's MAC as 1111. Now, that is not a full MAC address, not a legal MAC address, but we're just going to shorten all the MACs to 4 characters for ease of looking at it. Now, also, with that DHCP thing, we got a few other pieces of information that this computer has registered, and that is, one, its IP address, which we just talked about, 192.168.1.5. We also got a subnet mask, which you've probably seen before. That is something like 255.255.255.0. If you wonder what this means, basically, if you see a 255, that means that that part of the IP is a part of the network, and if it's a 0, that is a part of the host range. Now, you can see other numbers besides 255 and 0. We're not going to worry about those right now. Basically, all this means is that 192, that's part of the network. 168, that is also a part of the network. 1, part of the network. And then the .5 that we got is our host IP. So if we're communicating on this network, it's always going to have these first 3, what are called octets of the IP address. And in addition to the IP and the subnet mask, we also got some information, which is the default gateway. I'm going to designate that just DG. All the default gateway is the IP address of the device that data is going to flow through for other networks. So if we want to access any other network besides 192.168.1.whatever, it's going to have to go through this default gateway. And typically that's your 192.168.1.1, or the IP address of your router. And then the last piece of information that you would have got from DHCP is your DNS server. And because we're using this all-in-one routing device, 192.168.1.1 is also going to be our DNS server. Now, what does DNS do? Glad you asked. Let's take a look at something with DNS involved. Now I'm going to erase this, but just kind of remember, 192.168.1.1 is the default gateway and the DNS server. and our subnet mask means 192.168.1 is our network portion of our IP address. So let's try and go to google.com. So you open your web browser on your computer, you type in google.com. What's that going to do? Well, your computer has no idea what google.com is. That is just a word and these symbols that a computer doesn't understand, which are called letters. It doesn't care about that. It needs an IP address of the destination server. Google.com right now means absolutely nothing. So your computer is going to form communication to the DNS server to decode this. And all a DNS server does is it keeps a big table of names like this and their associated IP addresses. And we'll just say Google's is 100.1.1.1. It is not in real life. That's for the sake of example. So your computer forms this initial communication with those four things that we need. Source IP, we got that, 192.168.1.5. Destination IP, well, we don't know Google's, but we know our DNS servers because of what we got through DHCP. So destination IP is that 192.168.1.1, or the IP of our router. We have our source MAC address, 1111, but what is our destination MAC address? Well, our computer's not really sure what the MAC address of the DNS server is, so it's going to do what's called an ARP, and that stands for Address Resolution Protocol, and its purpose is to map an IP address to a MAC address. So it's going to send out this information with everything filled in for the source destination IP and the source MAC, but again, it's going to send out that destination MAC is all Fs, and that's going to go to everything on the network. So if we had other stuff connected here, that data is going to go up to our router, which will hit actually the switch portion. That'll get registered in the MAC address table again for PC1 is at 1111, and then it's going to send the information out every other port connected to it, except for this one, because that's a WAN connection. We will differentiate that in a minute. That's technically not a part of the same switch. And then whatever device sees this packet and is like, oh, well, .1 is my IP address and you don't know my MAC, it's going to respond with its MAC address. And that, we already know, is going to be the router itself. So the router sees that information and it sends it back, forming its own communication with the four things. Source IP being .1 now, destination IP being .5, source MAC being the router's MAC address, we'll just say 2222, and destination MAC address it gets from the original packet it got, so it knows that PC1's MAC is 1111, sends that info back. Now we have everything we need to communicate with the DNS server, which at this point we still haven't got to Google yet. We're still trying to figure out what Google's address is. But now we have the MAC address of the DNS server, so we just make more communication filling out these four fields again. Source IP.5, destination IP.1, source MAC 1111, destination 2222. And then that's going to go up to the router. It's going to query the DNS server. It's going to send back the information with google.com's IP address, which we said I think was 100.1.1.1. And then at this point, our computer is just going to do the same thing over and over and over again for this communication. So getting to Google, fill this out again. Source IP.5, destination IP is that 100.1.1.1. Source MAC 1111, destination MAC, oh no. What is google.com's destination MAC for 100.1.1.1? Well, we don't know, so guess what we're going to do? We're going to ARP again. And like I said before, that's basically all of this information, but with all Fs for the MAC, looking for the MAC address that corresponds with 100.1.1.1. Now, you might see a little bit of a problem coming, because when that traffic goes up to the router or switch, and it sends that out to everything else on the network, they're going to look at it and be like, okay, that is not my IP address, so I just drop that traffic. I'm not going to respond because I'm not giving you my MAC address when that is not who you're looking for. And nothing on our local network is going to satisfy this requirement because nothing on our local network is 100 dot. So what do we use for destination MAC address in this case? Well, this is where what's called Proxy ARP comes into play. And that's basically just a function that your router does when it notices that some traffic is destined for a network that it doesn't service, basically. So your router sees that packet, is comparing everything. It's like, well, this isn't my IP address, but I notice that it's come in on my interface for 192.168.1. whatever. So it's definitely never going to find this on the local network, so it's probably going to need some help. So what the router does is it sends a response back to the computer with its own MAC address as the destination. So here we end up with 2222 as the destination MAC for Google anyways. And then that communication gets initiated once again, goes up there with all of this new info, and this time the router is going to consult its routing table to look for this 100 dot network. So what a router needs, let's kind of go up here, get a little bit more room. A router has to have an entry for every network on the internet. Now your typical home router routing table is going to be this. 0.0.0.0 just means literally any IP address or network that is not in the routing table. This is called the default route, and that contains the IP address of a router that should know more. And that is pretty much always your internet service provider's gateway address or whatever your router is connected to on the internet side. So this guy. And then it has the entry for your local network. This is usually the only two things in the routing table of most home routers because it's only servicing one network, 192.168.1.0, so it knows where that is, and anything else it's going to send to the ISP. Now technically it would have a third entry, which is the link between itself and the ISP, but we're just not going to concern ourselves with that. The main idea is that anything that's not on the local network, it's going to send to the ISP. So again, let's expand this picture to include our ISP routers. So now instead of thinking about the internet as a big cloud of nothingness, you can think about it as a ton of routers connected together to get your traffic where it needs to go. So we're going to turn that cloud into router for our ISP, and we're going to say that this link between our router and our ISPs has the network 2.1.1.1. So again, everything on the internet's got to have its own IP address, and pretty much every little network has to have its own network address. So we would apply the same logic to this IP address, say maybe these are all the network designation, and then this is the host ones. So 2.1.1.0 would technically be the network. We'll say our router is .2 and our ISPs is .1 within this 2.1.1 network. So when our router consults its routing table, it sees, well, this 100.1.1.1 for Google is not a part of that network, so let's send it to our default route. And then guess what it has to do? It has to form those 4 pieces of information. Yet again, you better get used to this because this happens literally at every point that data flows. So between our router and our ISP's router, this is going to happen. Between their router and the next one, this is going to happen. Between that router and the actual Google server, this is going to happen. Now, source IP, you would think is going to remain the same, 192.168.1.5. It's not, because of what we talked about earlier and private addresses. So your router knows 192.168.1.5 is not going to be able to be used on the internet. And because of this, it has something configured called NAT, or Network Address Translation. What this does is it creates a second table in your router called the NAT translation table. And basically all that does is take the IP address of one of your internal devices, so .5, 192.168.5, and it'll assign that what's called a port number. Now at this point, I will say we are getting a little bit into layer 4 information that I did not cover, but a port is usually appended on to the end of an IP address which is usually something between 1 and 65,000 something. But typically this designates like what service it is going to be using. Like destination port 53 is for DNS, destination port 80 for web, etc., etc. But what NAT does is it assigns it just kind of a random value, say like 52,700, and now any communication that the router gets back with a destination port of 52,700, it knows came from .5. So this is how NAT is able to take a whole lot of private IP addresses on the inside of your network and convert them into a single public. It's just because it maintains a table of private IPs to specific port numbers, and when it sees these port numbers come back, it knows what internal device to send it to. So all of that being said, the information that the router is going to use is not going to be the private address. It is going to be a source IP of 2.1.1.2, which is our router's public IP address. And technically, it would append that port number onto the end of 52,700 just to designate that entry in the NAT table. Its destination IP 100.1.1.1 for Google, that remains the same as the original. Now its source MAC address, it is going to strip that off and change it to its own source MAC. And then it is going to be like, well, what's the MAC address again of 100.1.1.1.1? Because remember, it proxy ARPed to give its own MAC address to our host. So our router is not going to be able to use its own MAC address as the destination because now that has become the source. So it's going to do the exact same thing. It's going to ARP for that towards the ISP. The ISP router is going to look at it and be like, well, yeah, that's a different network. That is not a part of this one or any of the others that I service. So it is again going to proxy ARP back with the ISP router's MAC address. And then the cycle just continues. Our router will rewrite that 3.3.3.3 and send that on to the ISP router, which will do all of this again. The only difference now at the ISP level is that our source IP address is not going to change because we are no longer doing NAT. Now, I'm not saying it can't change. The ISP could also do its own NAT at some point in the process, but let's not worry about that right now. Let's say that these are just not going to change. 2.1.1.2 is going to be your source IP. 100.1.1.1 is going to be your destination IP until we get to Google. The thing that's going to change at every single hop is going to be the source and destination MAC address, with each router responding with its own MAC to fill out those 4 fields and then getting the information sent back, and so on and so forth. And if there's any switches in that, then it behaves the exact same as this one down here, where it floods it out all of its ports and looks for the MAC address. So let's go ahead and say we get all the way to Google. I'm going to go ahead and say that we went through like 2 different routers to get there. And then now we have hit Google's data center. And we have a massive switch with tons of servers on it. But this one over here is google.com. So this router here will be the last one in this long chain of communication. We're going to say that its IP is 100.1.1.2 just because we said Google was .1. I mean, in reality, .1 is probably going to be Google's gateway, not the actual Google server, but that is beside the point. This router receives that traffic, and at this point it still has the same source IP of .5, the same destination IP of 100.1.1.1, but now it has a source MAC address of whatever this guy's was, so we'll just say 7777, and then the destination MAC would be the MAC of this router itself. We'll say 8.8.8.8. So at this point we're going to have to do the exact same thing, formulate the packet to get to the actual Google web server. So how do we do that? Well, all of this remains the same. We are going to swap the source and the destination MAC. So source becomes 8.8.8.8. Well, 8888. Don't confuse that with the IP address of Google's DNS. This is a MAC address designation for this example. And then we've got to figure out our destination MAC again. So our router sends that out. It ARPs, again, with all Fs, looking for whoever has 100.1.1.1 to send its MAC back. So it hits the data center switch, that floods it out to every other web server on that same network in the data center. They all look at it and they're like, nah man, I'm not 100.1.1.1. This guy gets it and is like, I am. So then it sends that traffic back. Because this switch has the router's MAC as well as now the Google's web server MAC in its address table, it's not going to flood that out all the other ports on the return traffic. It's just going to go straight back to the router, which will again rewrite everything with the final destination MAC address. Our traffic will get to google.com. It'll do whatever things do when they get to google.com, and then it will flip everything. So in response, source IP is now 100.1.1.1. Destination IP is going to be 2.1.1.2, or the IP of our home router, public IP of our home router. Source MAC, whatever, 9.9.9.9, and because it has the destination MAC already, because it had the packet that came in, it knows 8.8.8.8 is the destination MAC address to send things to, and then everything happens in reverse. The only exception is that because all of these devices have done this communication already, they should have the source and destination MAC addresses already in their tables. So really it shouldn't have to ARP on the return trip at every hop, but every hop is still going to strip the source and destination MAC and change those to the device specific MAC addresses. Now once all of that has happened in reverse, going back through the Google data center, over routers, back to our ISP router, back to our home network, our router receives the following information: source IP 100.1.1.1, destination 2.1.1.2, or destination IP rather. Destination MAC is the router's 2222, or sorry, that is the source MAC of our ISP, so 3333, destination MAC 2222. Now, the router sees this 2.1.1.2 and is like, well, that's my public IP address, but yeah, I didn't request this information. What is happening here? I'm not talking to Google. Oh, wait, let me look at my NAT table again, and I see that the traffic I received is going towards port 57, or whatever we said, 52700, I think. Oh, I have an entry that says 192.168.1.5 was communicating using that port. Then it rewrites the packet. Source is going to be its internal IP, 192.168.1.1. Destination, 192.168.1.5. Source MAC, yep, it knows its own. And it should have our PC's destination MAC already still in its switch's MAC address table. Then that traffic goes straight back. So I already know that I lost most of you guys probably about 15 minutes ago, or if not at the very beginning of the video, but I thought that I would just kind of make this to roughly go through all the things that happen in a home network and beyond, just to kind of see how traffic flows, what all has to happen for communication to go through. And as you can see, there is a lot of different mechanisms, protocols, and whatnot that has to happen just between you typing in google.com and seeing the web page. This whole process of swapping out the source and destination MACs and ARPing and finding out the IP address through DNS and all of that happens hundreds of times before you can even blink your eye, which is really crazy to think about. But if you kind of know all of these underlying mechanisms and how traffic is really like supposed to flow through a network, you can start troubleshooting when things don't necessarily work the way that they should. So when you're on your computer and you type in google.com and it's like, well, we can't find that. All right, well, what was supposed to happen? Well, we were supposed to contact the DNS server to get the IP of google.com. Did that happen? If we open up command prompt and we try to ping google.com and it says, oh, we don't know the IP address, then guess what? You're probably not talking to your DNS service. Or you try to communicate and it's like, the network doesn't work at all. Well, what do we need? We need a source IP address, destination IP, source MAC, destination MAC. If I go into my computer's configuration and I see that I don't have an IP address, then it's probably DHCP, because I can't communicate if I don't have an IP address myself. What happens if all of that appears to be working fine? We get Google's IP address through DNS. We have an IP that we got through DHCP. We can ping our default gateway, and we can ping the other side of our home router, but nothing else here works. It's like the internet doesn't exist. Well, you might want to make sure that you are NATing properly, because if your IP address, well, private IP address, 192.168.1.5, gets used as the source IP address once you get onto the public internet, none of these public routers have a route for 192.168.1.5 because it is a private IP address. Now that one is a little bit rare. Usually if you can ping your gateway on your own router but nothing past it is because your ISP has screwed up, but you can check your own stuff first. And you can also explain why things like a broadcast storm happens. This video is already long enough, but let's go ahead and look at something really interesting which we can explain using everything we've gone through already. Let's say we've got a switch. Our PC is connected to that switch. We have a router over here. But somebody went and connected port 1 to port 4. Or we'll say port 2 to port 4. Whatever. We connected the switch to itself. So what happens? We got those 4 pieces of information. Source IP, we'll say it's still .5. Destination IP, whatever, doesn't matter. Source MAC 1111, destination MAC, the router. That goes up to the switch. If it needs to ARP, then what's the switch do? It sends that info out every port except the one it came in on to find out the destination MAC address to be used. But what happens? It sends that out here to the router. It sends it out port 2. Oh, and it sends it out port 4. So what happens here? This comes around here back to port 2 with a destination MAC of all F still. So what's that mean? It's going to forward it out every port that it didn't come in on. Guess what? Now it goes back this way. It goes there. But also, switch 4, or not switch 4, port 4 received the same thing. So what's it do? It floods too. Guess what? It's sending it this way, as well as sending it back to itself from port 2. And I think I missed it, but port 4 would have sent it back to port 2 during port 2's flood. And what's that do? Oh wait, that initiates the same thing over and over and over. So you get this storm. It's what we call a layer 2 loop, where all the traffic just goes between the switch ports and gets flooded everywhere. And this is when your network comes to a complete stop, because your switch is just overwhelmed with as much traffic as it can possibly put out, due simply to the fact that it was connected to itself during all of this. Now, there are mechanisms in place to prevent this, but it does still happen. If you've heard of spanning tree, that is a whole other protocol that happens at layer 2 or in the switch area that is designed to prevent loops like this. And there are also routing loops as well. Those can come about with improperly configured routing tables. Say one router has a default route pointing towards another router that has a default route pointing back towards that same router. You get about the same thing happening. But you can kind of understand why these types of storms and these issues happen when you understand really the basic flow of information through a network. So I know this one was extremely long-winded, extremely convoluted, and probably really hard to understand. I did my best to kind of break it down and make it not so insanely in the weeds, but while still giving you a lot of information. Let me know in the comments if it worked out that way or if this was just a big failure. I hope you learned something. Let me know if you want me to make anything else kind of like this. As always, Happy networking.